Okay, good afternoon, everybody. For those that don't know me, I'm Jane Hilston. I'm currently Director of the Laboratory for Foundations of Computer Science. The Milner Lecture is an annual event within the LFCS, which was supported by a bequest, or I guess an endowment, from Robin Milner, who was one of the founders of the LFCS. He stipulated that this should be a talk given by somebody from outside the university who has done or is doing excellent and original theoretical work which has a perceived significance for practical computing. The spirit of the proposal is to keep a live connection between theory and application in computer science. I'm very pleased today that we can welcome Marta Kwiatkowska from the University of Oxford to give the Milner Lecture. She is a prime example of somebody who works at that boundary between theory and practice, making sure that the theory that she develops has real practical use within computer science. So thank you very much for coming today, and we'll look forward to your talk.
Thank you, Jane. I am greatly honored to be this year's Milner Lecturer, and I am very grateful for the opportunity to tell you about my research, where it is heading and its future challenges. And I would like to say that this research was actually greatly inspired by Robin Milner himself, who was tirelessly working on making us aware of the need of the science for ubiquitous computing, or Ubicomp. He didn't like ubiquitous computing. This was too much of a mouthful. So I would like to offer this lecture as a tribute to Robin. So let's start. The first thing I would like you to do is to pause and consider a typical city scene, which could be Edinburgh, could be Oxford, could be Beijing, and ask yourself the question, where are the computers? Of course, once upon a time, that is back in the 1980s, PCs and mainframes dominated the world. And they used peripherals such as floppy disks and keyboards, or even further back, tape and card readers. But today, the world has changed. Smartphones and tablets are taking over the world. There are 5 billion mobile phone users, particularly in the third world countries in Asia, and they are all sensor enabled. They have sensor apps that can read GPS. They contain accelerometers, but they are also used for some more esoteric applications. For example, they are connected to air quality sensors, or they can even monitor your sleep to make sure that the alarm wakes you up in the right sleep phase. They give you access to all the personalized systems. And in fact, smartphones are apparently rivaling the television in the fastest spreading technology of all times. Now, look at the home. And in the home, the appliances are networked. I'm showing you an example of a device which is currently on the market. I would say that whether you need a fridge that tweets, well, it depends on your taste. Perhaps it's not the most important application, but it is an important step for internet-enabling home appliances. That fridge in the future will be able to perhaps automatically order your milk and negotiate the best price for it. These days, there are services being offered for remote control of energy services, not just your hi-fi. And then there is intelligent transport. You may have been on the Heathrow pod, which is a fully automatic train connecting the terminal to the car park. What this is actually a Ford Focus, which was released this year. And for people like me, it's amazing because it parks itself. So what you could have seen there is that it turns the wheel. It actually looks for a parking space and turns the wheel. On top of that, what it can do is it can actually provide assistance in traffic jams. So it will brake, you know, when you are getting too close to the car in front of you. And then if we go further, there are many, many medical devices. I'm here showing you examples of two. The wearable shed is on the market and provides all kinds of monitoring connected to your smartphone, of course. The watch is actually connected to an implantable glucose sensor. It's not on the market. It's going into trials. It's intended to be released in 2017, but what it does is actually monitors the glucose levels, sends them wirelessly to the watch, and then alerts the user. So basically, the examples that I've shown you are nothing but ubiquitous computing. Ubiquitous computing is computing without computers. They've disappeared. This is also known as pervasive computing or Internet of Things. Internet of Things refers to these home appliances that are Internet enabled. And in fact, ARM, our company ARM, has started the UK Industry Forum to try to develop the Internet of Things in the UK. Now, all these developments here are not just the result of tremendous progress in sensor technologies, but also cloud and wireless technologies which are providing invisible support. So computers are not here. I mean, maybe they are in your offices, but there is a lot of computing which is being done all around you. And it's done by devices which are embedded in the environment. They are sensor-enabled. Critically, they are software-controlled, and they operate unattended, autonomously. They are mobile. They are handheld, wearable, they might be even implantable, and they are miniature in size. And on top of that, they are organized into communities, social networks, etc. And as the technology progresses, what we will see is even more and smaller devices. So ubiquitous computing is a term that was introduced. In fact, it was conceived in the late 80s by Mark Weiser of Xerox. His papers appeared in the early 90s. Now, he described it as the calm technology. The most profound technologies are those that disappear, and that has certainly happened. Then from the usability perspective, Adam Greenfield started asking a question. Well, if this is my household appliance and it can do computing and information processing for me, what should I call it? It's not hardware, it's not software. So he came up with the term everywhere. Note the spelling, there is no typo in there. And of course, Robin Milner himself was a great proponent of the science of ubiquitous computing, and he was trying to make us develop the tools, theories, models, and various other techniques to support the development of Ubiquitous systems. So what I'm going to talk about is my group's and my collaborators' contribution to that, which is focused very much on taking the theory to practice, and in particular developing algorithms, practical, theoretical, and practical algorithmic implementations. and industrially relevant tools. So because in the Ubicomp world, software is what makes the device compute, wherever that device is. What we need is we need strong methodologies for developing software that is high quality, safe, dependable, reliable. And I specifically mention here techniques such as model-based developments, rigorous software engineering, and software product lines. From my own personal perspective, I work on formal techniques, but formal techniques which aim to automatically establish that certain critical, important properties of Ubicomp systems hold. And I mention here a couple of examples. Safety, which is the probability of failure to raise alarm, is low as you need it. So this talk is going to be centered on automated verification via model checking, and I'll say a little bit about this, and in particular on quantitative verification. And again, I'll try to explain what I mean by this. Now, rigorous software engineering is a methodology which involves working from informal requirements towards developing formal specifications, and then the actual software or systems, but they are derived from models, or perhaps you extract a model from the system. Now, my contribution comes here. It is verification. It is verification of a formal specification against a model. And it is something that enhances software engineering. It does not replace software engineering or other dependability assurance approaches, but it enhances it, and I hope to show you in the course of this talk in what way this happens. So I promised to tell you what quantitative verification is. I put probabilistic verification in brackets because my personal focus has been on systems whose dynamics is described probabilistically. So they move according to probability distributions, perhaps according to some coin tosses. We start with a probabilistic model which is derived in some way from the system. There could be an involved modeling process, or perhaps you can extract it or derive it from the standard. And you also have to give it a specification. Now, because the system is probabilistic, this specification is also probabilistic. And this P here means probability. And this property says the probability of eventually, F means eventually reaching fail in time t, is bounded from above by 0.01. So it's small. Now, if you input this into a probabilistic model checker, what that model checker can produce is an answer, and an answer which says yes or no, the property holds. If the property doesn't hold, it can also give you a counterexample, which is a trace to error. But in addition, it can produce quantitative results. So these are plots for different parameters in the model of some important measures characteristics of the system. And these could be energy usage, for example. Why do we want quantitative verification? Well, because real Ubicomp systems and software actually are quantitative. There is no escape from it. Maybe they don't necessarily have probabilistic dynamics, but you have to consider probability when you want to analyze failure. They often have real-time aspects, hard and soft deadlines. They have resource constraints because they have small memory, small processors. They tend to be battery-powered. They use randomization because in large populations, in distributed systems, randomization is very useful to manage a system without a central manager. And of course, there is a lot of uncertainty. It's not just failure, but uncertainty in communications, for example, because they tend to be connected by wireless. We know that wireless messages can get lost. So this is the main reason why we just can't escape quantitative verification. But the advantage of quantitative verification is that it gives you the strength of a mathematical proof that the property holds for the model of the system that you have developed. And what I mean by this, in addition to being able to analyze best worst case scenarios, in this plot here, the blue and the green lines represent the minimum and the maximum values. That means that these areas are ruled out. These areas are ruled out. That's what I mean by a mathematical proof. What you have here is validation, which is a simulation run, demonstrates one possible run of the system. Okay? But the model checker has already pre-computed the red and green values. And these are very useful and also very useful in identifying trends and anomalies in systems. To give you some examples of quantitative properties, what I'm showing here on the left is a temporal logic notation, but on the right you have a sentence in English which to those who are not familiar with the logic will also give you an example, an idea for what these properties are. So here is worst case probability of an outage occurring within 10 seconds for any possible scheduling of system components. It is something that you may want to establish for a protocol. Or if we are talking about cars and automotive and airbags, the maximum probability of an airbag failing to deploy within 0.02 seconds from any possible crash scenario. In addition to properties which compute probabilities, what we can also compute is expectations, expected time, expected costs, expected rewards weighted by these probabilities. And these are denoted by the R operator, the rewards operator, which is parameterized by a reward structure. And inside, it also tells you about the paths over which you compute the expectation that you want satisfied. Eventually, the algorithm will reach a state marked by an end. So these are real examples of properties that have been used in actual practical implementation of practical application of quantitative verification. Now, for the historical perspective, there seems to be a theme, 1980s, in this talk. The area of quantitative probabilistic verification actually started in 1980s with papers by Bradycardia, Ubiquitous, and Yanakakis, and it was very soon followed by the first algorithms and very first implementations. But it wasn't until 2000 when there were two tools released, and PRISM is the tool that I'll mention, I'll say something about later, and another one is ETMCC, now known as MRMC. So these tools were developed in a way that it was possible to use them by non-experts, and they have been successfully used. There are now over 300 papers from various people, academics and industrial users of PRISM who have used it in many, many application domains, which I mention here. So I claim that this is now a mature area, relatively mature area, which is of industrial relevance. And there have been genuine flaws which were found in real protocols and examples. Now, what do we need to do in order to do quantitative verification? So if you remember the picture, we input the model and we input the property. So the first thing that the model checker has to do is to actually read the description of the model and build an internal representation which can then be algorithmically analyzed when we are checking the properties. Now, this analysis involves conventional non-quantitative model checking algorithms which analyze the underlying transition system, the graph structure of the system. And in addition, it has to involve numerical solution. Because we are talking about quantitative analysis, we need to be able to calculate probabilities and expectations. So typically, this is more expensive. So I'm trying to sell you a tool which is more computationally expensive than a conventional non-quantitative model checker, but my point is that we can't escape quantitative verification. Now, there has been some progress made since 2000 in quantitative and in probabilistic verification, my personal domain. So there has been an extension to probabilistic real-time systems. We have abstraction refinement, probabilistic counterexample generation, and some compositional verification. But one thing that we have not managed to improve is the size of the state space that we can handle for a single monolithic system. It is still stuck at this 10 to the 7 or 10 to the 10, depending on the structure of the model. But tool support exists, and as I've mentioned earlier, it is actually being used, and it is used quite widely. And the tool that I have led the development of, starting at Birmingham and at Oxford, and now it's shared development with Birmingham because Dave Parker, who is the implementer of the tool, has now got a lectureship at Birmingham. It supports 4 different types of models and several temporal logics with which you can specify the properties for these models. And it also supports this quantitative analysis based on the rewards, the expectations. And it has many connections, in particular a local connection here to BioPepper, and I'll say something about some of the other connections in this work. If you are interested, there is a link. And with this tool, PRISM, there have been some successes. I've mentioned flaws and unusual trends that we discovered in real-world protocols. So one of the first case studies, which is still very appropriate for ubiquitous computing, is the Bluetooth device discovery protocol. The model was developed straight from the standard, and it was absolutely huge. It was so huge that the analysis had to be divided into 32 separate Markov chains. But what this analysis was able to show, that the worst case time to hear one message between two devices is about 1 second. It was very, very high. Okay? The expected time is much, much lower because this worst case time happens in a very small number. This is something like a rare event. So this was one example of a success. Another example is work that we did jointly with biologists, where we performed so-called in silico experiments. We developed a model of a molecular signaling pathway, and then we guided the biological experiments by doing the models, the analysis computationally in silico. And that led to a prediction which was then validated by lab experiments. So these are two examples, two concrete examples of successes, but we are now faced with the challenge of ubiquitous computing. And it is a huge challenge, and at times it seems insurmountable. And I think I will try to point out some numbers to indicate that we need a lot of research in order to make progress in this area. So what I have done for the remainder of the talk, I have selected 3 specific examples that are from the ubiquitous computing domain, and these are this is work research that has arisen from my group, and in each specific case, I will demonstrate that there is a transition from theory. Theory is absolutely essential. You have to start with theory. You have to start even with a theoretical algorithm. But then the effort is also put into developing actual software tools, and software tools that can be used by non-experts. And in each of these cases, there has been a new software tool, some kind of extension of PRISM, and they are all very different extensions. So the first example will focus on modeling cooperation and what kind of models and techniques are needed and what the guiding examples are. There is another which will focus on monitoring physical processes, for example, electrical signal, etc. And the last one is going to look more towards the future and how in future we might be able to connect to biological systems. So here are the 3 examples, and I'll try to stay at a fairly high level. I have simplified the talks. If anyone is interested, I can point you to the research papers. I can also discuss and explain things in a bit more detail. So first of all, Ubicomp, as I've already mentioned, Ubicomp systems are basically populations of these autonomous sensor-enabled devices. And these tend to be organized into communities. So what we have is we have no longer agents in the sense of CCS. We have agents which have self-interest, and they have their own goals. They may want to maximize the profit or perhaps minimize the battery power usage of your smartphone. I think that's more likely. Now, what they need to do quite often is to cooperate, because, for example, in a network, in a wireless network, we have to share, so we have to agree to share, and we may have possibly opposing goals, because we may want, too much energy or too much bandwidth. So it is well known that incentives are needed in order to manage such situations. But there are many, many scenarios. There is a new initiative called user-centric networks being developed. Energy management and sensor network coordination are very specific examples. Now, because of this introduction, those of you who are familiar with economics would say, well, why don't you use economics games? And this is precisely what we are going to do. We are going to involve stochastic games and game-based techniques in order to enable the analysis, the quantitative analysis of such systems. But the focus will be different. So rather than focusing on, say, mechanism design, as people do in AI, what we are going to do is to develop algorithms and tools. So I'm going to show you a tool that can be used to automatically verify cooperative behavior. So I'll start with a motivating example. And the example is the notion of a microgrid. So what a microgrid is a unit, perhaps a number of households, perhaps the university. And the idea is that that unit manages its own energy in a localized manner and also in an autonomous way. So this unit may receive energy from the grid, but may be disconnected from the grid, may also receive energy from wind or solar, and all this has to be balanced with demand. So we need active management of demand by users, and of course we want to avoid peaks, because peaks are very likely to cause shutdowns. So microgrid demand-side management is a growing area, and there are a number of protocols that have been proposed to actually do this management. So what I'm referring to here is a specific protocol which comes from BT, and it was actually informed by a case study performed on real households, where they have developed this daily demand curve. Now, the idea of the microgrid is that each household wants to maximize its own value, but of course, at the same time, you want to minimize the total energy cost. And this is where we need to balance things. These authors proposed a very simple algorithm, and this algorithm is probabilistic. So if the cost of performing this task is below an agreed limit, then you execute it. Otherwise, you just execute it with some probability to randomize. And what they then did is they did a simulation-based analysis which showed reduction in peak demand and also total energy cost, but this was all providing all households stick to the algorithm. So the question that we asked ourselves is this algorithm able to prevent selfish behavior? And you can probably guess what the answer is. So what we used for that is we are working with a stochastic games model. Stochastic games, this is a specific variant. They are called turn-based games. So we have states partitioned amongst a number of players, in this case a household, each household, and they each take turns. So once this one has made the choice, then that one will respond. And what we want to do is we want to consider these stochastic game-based models where each player corresponds to a household, and we want to analyze the behavior for certain subgroups of players with respect to all all the other households. And in this particular case, you can show that these two players can actually prevent the yellow circle player from obtaining a higher probability. So the idea is that these two collaborate and they compete against that, so the other one. So what we have developed for this is a logic. Now, those of you who are familiar with temporal logic may be aware of the logic ATL, which is called alternating temporal logic. And that logic allows one to specify a coalition and analyze the behavior for a specific coalition. But that logic doesn't have the probabilistic operator and the reward operator, and this is what we have done in this work. So we have essentially combined ATL with the logic PCTL, which provides these operators. And what we can do, and this now extends the functionality, the quantitative properties that I showed you earlier, we can now specify properties like players 1 and 2 have a strategy to ensure that the probability of an error occurring within 10 steps is less than 0.1, regardless of the strategies of other players. And this is another example, but now I'm using the rewards operator in a quantitative fashion. So what I want to do is to obtain from the property and the model the minimum expected energy that the system coalition can conserve, no matter what the other players do. You may have noticed that we use the existence of the strategy in the informal description of the properties. So indeed, we define the semantics using the existential form, but how do we do it? We assume that we have a multiplayer game, say one player for each household, but we want to analyze only certain coalitions. So for the analysis itself, what we do is we reduce the multiplayer game to a two-player game, where the first player is the coalition and the other player is everybody else. So you start with a multiplayer game, you reduce it to a two-player stochastic game for the analysis, and this is the formal semantics, and the semantics for the reward operator can be done similarly. And what can we do with this? Well, we could analyze the microgrid demand-side management, and in particular the simple algorithm that I showed you. This was the daily demand curve, which actually came from the actual observations of the households. Notice we have analyzed up to seven households, so we have a long way to go. But what we were able to show, perhaps unsurprisingly to those of you who are familiar with games, is that this simple algorithm actually does not tolerate deviations. And I can show you the simple plots. So this is where all households follow the algorithm, and I'm showing here the lines. So the lines, the width of the line depends on the size of the coalition. So notice that the smaller coalition, the more gain they can produce for themselves, okay, individuals, but of course this would be at a cost of total energy cost going up, which is not shown on this plot. To show you that the algorithm can be improved, and in fact can be corrected, what we allow is not just incentives, but also disincentives. So we punish households for bad behavior, And under a simple punishment mechanism, what we managed to do is to show that now this algorithm is really behaving very well. So if anyone is interested, there is now an extension of PRISM, which is called PRISM Games. And this extension actually provides an additional model, stochastic games, SMGs, which is supported by PRISM, and the logic that I have briefly introduced. And there are a few case studies, including also collective decision-making for sensor networks. So this is the first example. Now the second example comes from a completely different area, theoretically speaking, and I am referring to this as the physical processes because I am going to tell you about monitoring of an electrical signal, but in fact the application is in a medical device. And that medical device that I will use is a cardiac pacemaker. So Ubiquitous systems also need to monitor and control physical processes and electrical signal, etc. The difficulty and the difference to the previous example, where I was only working with discrete probability distributions and discrete states and, discrete values, what we have is we have to be able to describe the behavior of these physical processes, and it tends to be given as nonlinear differential equations. And I'll show you some examples here. So we actually need to model continuous flows, but then in the system, we are going to have the software that manages this, and we have to, in order to do verification, we have to compose the system with these continuous flows. So the natural model to use is, of course, a hybrid automata, hybrid system model, which allows continuous discrete mode switches and also continuous variables. And probability comes in as a minimum when you have to consider failure. You also have to add probabilities. There are lots of ways in which you can add probabilities to hybrid systems. And here I'm only going to show you a few simple, very simple ways. So I'm going to show you some recent work that we did on doing the first quantitative probabilistic verification of pacemakers. So I need to start with telling you a little bit about the heart. The heart basically maintains blood circulation throughout the body, but it does it by generating an electrical signal. And that electrical signal originates here, and then it is passed along the pathways, which are shown here, and then the atria and the ventricular contraction happens, so the blood empties the heart, and then this process is repeated. So it is a real-time system, because these electrical signals have to come at certain time periods, and for a normal heart, they are between 60 and 100 heartbeats. So this peak in the signal actually corresponds to a heartbeat. Now, there are, of course, various abnormalities, arrhythmias, and some of them can be corrected by implantable pacemakers. Now, how does that pacemaker work? So unlike the glucose monitoring device, it is a wired device. The glucose monitoring device has a wireless connection. This one is wired, but you have sensors placed along the leads, one in the atrium and another one in the ventricle. And the pacemaker reads the electrical signal, and it reads the signal which it is on the, in the heart, and it's known as action potential. And it monitors the timing and generates artificial pacing signals as necessary if the heart is too slow. Now, unfortunately, I mean, this is a well-established technology. These people, you know, these devices are widely used. But as you can see here, firmware problems tends to mean software problems. So we do want to bring in verification. But of course, because there is so much variation in different heart behaviors from person to person, testing and validation is also extremely important. So I'm showing you here a system that was developed at the PRISM Center at the University of Pennsylvania. And what they have actually done is they deployed an FPGA, but FPGA runs the software. To this, they connect the real pacemaker, and they also provide a model. It's a model of the heart, which can be used, but it cannot be used for verification. Okay? So what we want to do is we want to start a program where we would like to enhance the framework with quantitative verification for a pacemaker. Now, here, there is a lot of help around because there are various approaches and various models that exist, and in particular, there are timed automata models of the pacemakers which were developed at the same place at the PRISM Center, and this is what we have adopted. But if you think about it, this pacemaker needs to be connected to the heart, and the heart, as I showed you, generates this nonlinear ODE signal. So what does verification mean? And in fact, we have not yet fully answered that question, but we can verify certain properties, and I'll show you what they look like. Now, the reason the correctness is difficult is because the heart rhythm is very variable, and in fact, it is very, very patient-specific. But fortunately, at the Oxford Biomedical Engineering Institute, there is a person, his name is Gary Clifford, and what he's developing is he's actually developing software to be run on smartphones aimed at the third world so that people can monitor their own heart, their own ECG using a smartphone. Now, for this purpose, he has developed a synthetic ECG model, and this model can be learned, can be adapted to the patient data. So if you have specific data for the patient, you can then use machine learning to adapt this. But this model uses chest surface measurements, which is not the same as what the pacemaker reads. So what this is the next step, I think, for our work. Of course, why does probability come in? Well, probability because you need to consider failures, but there are also probabilistic aspects in the way that the heartbeat varies for a person over time. So what we have done is in order to do the verification, we need to connect the model of the pacemaker with a model of the heart, compose them, and this is, and they are both I/O automata because the pacemaker will induce an electrical signal in the heart, so the pacemaker modifies the behavior of the heart, doesn't just monitor. For this, we adopt the timed automata models from the PRECISE Center, and we connect it to the Clifford synthetic model of the ECG, which we map to action potential, and the action potential signals are then used to synchronize with the behavior of the pacemaker. So what you can then do is you can show, but it's very hard to show the correct behavior. So here, notice that the purple lines here are the original heartbeat, and because they come at around 2 seconds, they are too slow, because the heart needs at least 60. What we can show you here is that the pacemaker will correct that heartbeat by inducing the extra green lines. There are additional properties that we can also check. For example, we analyze under-sensing, which is the situation in which the sensor implanted in the heart does not sense correctly, and how this affects the behavior. We can also analyze expected energy usage. And the tool is implemented in PRISM and MATLAB, but at the moment, the tool is entirely based on discretization. So we discretize the timed automata models using the PRISM digital clocks, and we also discretize the heart model. And it is very difficult to imagine what else we can do. But I think if we want to do quantitative verification, then that's a challenge that needs to be resolved. So for the final thing, we are going to look a little bit towards the future. So in the future, the idea is that Ubiquitous systems will need to sense and also control biological processes. So what we would like to do is to be able to program, perhaps even at the molecular level, things like, is this a cancer molecule, and if it is a cancer molecule, perhaps deliver some drug. And these ideas are already around, and they are being developed in a test tube in vitro. I think it's still a long way until they get into in vivo, but why not? Why not start? So what we are doing is we are focusing on DNA computation. Now, DNA computation uses DNA molecules. DNA molecules are very attractive because they are widely available. They also can store information, they can process information, they are relatively cheap to synthesize, so they are a very attractive material, and what people are trying to do with them is to design and actually build also in vitro computing devices. Now, this is not the same as synthetic biology, because in synthetic biology, what we want to do is we want to modify DNA of a specific bacterium, but there could be tools and techniques that could be applicable. So if I ask you to consider digital circuits, well, digital circuits are basically logic gates, but they are realized in silicon. And we have zeros and ones. They are encoded as high and low voltage. Now, hardware verification is indispensable in this context, and it is really used massively at an industrial scale. So the question that we want to ask here, well, can we do the same for DNA programming? Now, DNA programming is very, very different. So what we are dealing with is these DNA molecules. So this is the helix, which are very, very small. And computing happens in a soup. So DNA has this amazing property that if you carefully select strands, and in this example, what you put in the test tube is one long circular strand, and then very carefully chosen short single strands. All you need to do is to heat it and cool it, and then it will self-assemble into a pre-designed shape, in this case, a smiley face. This is known DNA origami. So I'm showing you this as an example of what DNA can do, but not necessarily as an example of the computing device that we started off with. Now, because we are computing with soup, basically we have lots and lots of molecules, and they are colliding randomly. Stochasticity is essential, so quantitative verification is, of course, very appropriate. And in fact, there are already techniques that have been developed at Caltech and various other places. This is a very recent result in May or June this year. They have built a circuit in this soup. So that's what the circuit looks like, but this is how it computes in this soup. And what it can do is it can compute the square root of a 4-bit number. So a number from 0 to 15, and it computes a rounded down. Well, it takes 10 hours, but but I can tell you, I have a collaborator across the road who has alternative methods to achieve the same result, and his is much faster. So DNA strand displacement is the technique that was used by Lulu Xian and Eric Winfrey. They used a slightly different variant of gates. They used seesaw gates. But Luca Cardelli, who is at Microsoft, and he was a collaborator on this work, he actually designed a precise algebra. So he gave formal semantics to a certain type of DNA strand displacement. And these describe reactions. These reactions you can put in a soup, but you can make these reactions compute. So if you throw in a certain number of input strands, you just wait for some number of output strands. And this is all technical. What you need to look out for is these toe holds. These are short domains, so they are really only a few, 6 to 10 bases. And what they allow you to do is for this single strand to attach here and displace another strand. And this is a transducer. This is a transducer gate, and that's the input. And I've taken a little video from Luca Cardelli's website, which shows you how the computation proceeds. So basically, it started with Tx and went through a number of molecular reactions and produced this output. Okay, that's output. That's how DNA computation proceeds. Of course, we are talking about large numbers of molecules, okay, in the soup. This is the full reaction list. And what you can see here is the output, and also the fact that there are some structures that are produced, some garbage. But in this case, this garbage will not create any problems because it does not have these overhanging toe holes, so it's not going to attract any other molecules. But there is a reason Luca has approached us, because he has designed the transducer gate, and it turned out that it had a flaw in it, and he realized that it had a flaw. So it works for a single gate, but when you put it in a cascade of 2 gates, it has a flaw, and this is known as the crosstalk. Now, apparently, people have tried to demonstrate the flaw through simulation, but they failed. So this is why he suggested that we try to use PRISM, and that's what we did. So in fact, PRISM can find this bag, the same bag, completely automatically, and it's only a 5-step trace to error. In addition, we can do quantitative analysis of the transducer gate. So for example, here notice this is the plot of the gate eventually terminating, but with probability 1/2, it will either terminate correctly or not. And notice that the error, actually the reaction that leads to error occurs earlier. So what we have done is we have now connected PRISM to a tool which is called DSD, and the tool has a programming language for DNA, so you can write DNA programs. It also has a graphical user interface. It was developed by Andrew Phillips, but now what it can also do is it can automatically translate the DNA designs via SBML into PRISM, and you can do the analysis. Well, you might think this is great, but if you ask me how many molecules are there in a test tube, the answer is millions. I think it is quite embarrassing how few molecules we can check here. The limit is about 6. So we have a long way to go. But if anyone is interested, then the tool is available. So this is the end of my talk, and I hope that I've shown you some hopefully interesting first successes and also useful applications of quantitative verification methodologies and some new tools and techniques. But I also hope that I have showed you that we have a long way to go before we can tackle the Ubicomp challenge that Robin Milner was encouraging us to do. So if anyone is interested, then I'm putting the references here, and I'll also make the slides available. And finally, I would like to acknowledge all the collaborators in this work, but also collaborators who have contributed to other pieces of research that I didn't discuss here, and in particular the many external users and contributors to PRISM. This work has come out mainly as part of my ERC advanced grant project called Veryware, which is from software verification to everywhere verification, and it is also a continuing research project about PRISM. Okay, thank you for your attention.
So I wanted to ask about the hybrid systems. At the moment, you completely discretize. Do you see any prospect of getting around that? Because you must expand your state space considerably through that process.
Yes, so if we work with discrete probability distributions, or, for example, discretize continuous probability distributions, then you can work instead with the polyhedra representation, and then you can obtain better results. But we haven't tried that. And for some of the features of the heart model, we cannot assume discrete probability distributions because the underlying rhythm has got randomness.
Fabulous talk. I guess I have a question about algorithms and about scalability. You didn't really touch on this, but I mean, what about parallelism and distribution? I mean, you gave some numbers, but I mean, is there hope that we could push these out onto the cloud and speed things up?
Yeah, that's a very good question. It's very easy to push simulation into the cloud. It's much, much harder to actually do the solution of, a CTMC, transient probability calculation. We have tried that, but it doesn't compete in terms of time, because what you need to remember is as the system grows in size, you might also need to send parts of the data structure, in between the cloud. So I have hopes for scalability in the following. Compositionality, but that is something that we are working on, but it's very, very hard in the probabilistic case, particularly in a probabilistic case when you have probabilistic dynamics. Then approximation, so good approximation methods for anything continuous, or some kind of hybrid solutions where you can, say, abstract certain variables to infinity. So we are working on this, but we do not have good results yet.
Yes, I also enjoyed the talk very much, but a slightly off-topic question. When we have these huge networks where every light switch has a sensor in it and is addressable, and maybe even every cell in your body or even unity, how do we organize the addressing of these things? I mean, how do we, this is just we can give everything a unique identifier, but so what? How does that help?
Well, I'm probably not the best person to answer this. I really don't have a good answer. I think I just assume that there will be someone further down the chain who can give a good addressing scheme to me. But I think the complexity of the Ubiquitous systems, as Robin Milner was referring to them, is incredible. It is. I mean, the problems are really insurmountable.
It reminds me of sort of a general comment. It seemed to me what you were saying was that a central problem, particularly with regard to biological systems, is continuous control. Is that right?
Well, yes,
or continuous flow, you put it.
Yes, that's right.
So you need to be doing things continuously in time. And it seemed to, what you were saying, it seemed to involve nonlinear differential equations, which presumably takes some time to actually compute. Yeah. So what my suggestion is that maybe you could learn something from, or more anyway, from biological systems, which clearly do control in a continuous way, and also, I don't think they solve nonlinear differential equations, okay? Like ants, for example, or humans, for that matter. So I was just wondering whether, you can feed into the modeling some knowledge from what the biological systems actually do, and have been very successful at doing it for millennia. Okay,
so I'm not sure I sort of fully follow your question. We do modeling of biological systems, and we use both continuous and also discrete stochastic methods. So we do try to model the behavior of biology. But I think what you are saying is that we should also try to maybe extract from, say, biological systems some aspects of their behavior that maybe would be useful in protocols. So, for example, okay, yes, so I think that's a very good point, yeah.
Thank you for your talk. I had a question about the verification of very large systems. So, you know, you have a plethora of sort of situations and inputs and states and interactions between all this ubiquitous devices. It seems that likely at some point the discrete verification of all this is just computationally infeasible. So I'm sort of wondering, where do you think one can go with that? I mean, I was thinking of particular cases, maybe verification of sort of security levels, where you can maybe validate access security for any individual device, but when you have, you know, 1,000 of them in your house, how can you say that the house is secure?
Mm-hmm. No, I mean, yeah, this is, yes, absolutely right. What I was talking about is offline verification. So once you have a design, you verify it, you analyze it, because you want to improve the design. But this is, in many situations, not acceptable. So if you consider large-scale systems, you consider adaptive systems where the requirements may change, the environment may change, and I think what we need there is we need runtime verification to complement all the other rigorous software engineering techniques. And I've already done some work on quantitative runtime verification, and in particular using offline verification to do steering. So you know, runtime verification means that you are monitoring the behavior of the system as it runs, but then you might want to steer it so that it avoids, you know, bad deadlock situations, or, you know, probably you know, these kinds of situations. I didn't talk about this, but there is a stream of work which is it's essential. Thank you.
This production is brought to you by the University of Edinburgh.